dean, faculty members, and my dear friends and participants. A warm welcome to all this for this program. So I am privileged to welcome today's speaker, Dr. N.V. Prasad Garu, Department of Physics, Osmania University, and also I invite Professor G. Pushpa Chakrapani ma'am. Professor G. Pushpa Chakrapani, I invite Professor G. Pushpa Chakrapani ma'am, HOD, Department of Physics, Dr. Ambedkar Open University. So I am very grateful to N.V. Prasad Garu for accept to give a lecture for this webinar. I will now hand over this session to our HOD, Professor G. Pushpa Chakrapani ma'am. Ma'am, we are welcoming this program, ma'am. I am handovering this program to you, ma'am. Thank you.
Thank you, Usha. Yeah, am I audible?
Yeah, ma'am.
Yeah. Good evening, my dear students, Dr. N.V. Prasad Garu and Dr. Usha. I welcome you all for this today's webinar on quantum mechanics and statistical mechanics with applications. First of all, please, I should apologize for not having started the program on time because there is a technical issue with the host. So it was delayed. Extremely sorry for all the students as well as Dr. Prasad Garu also. Students, thanks for joining this webinar. Dr. B.R. Ambedkar Open University always supports students in all the ways. See, apart from your classes, regular classes, online and offline classes, counseling classes, and University Department of Physics, Dr. B.R. Ambedkar Open University also planned some webinars, invited lectures by inviting different expertise people from different universities. So this is the fourth program that taken from Department of Physics. The three programs we have organized in the university campus itself for the students, and these two we have planned as a webinars. And this is the first webinar for the Department of Physics for this season. Here now we have with us Dr. N.V. Prasad Garu, Associate Professor, Department of Physics, Osmania University. He is a good teacher and also a good researcher. He has many national and international publications to his credit. Sir, thank you for accepting our invitation and accepted to give a lecture for our students today. I don't want to take much time because already we are delayed now. Sir, I request you to please start your lecture program. Thank you.
Thank you, madam.
Yes, sir, you start.
I'll start. Madam, is that clear now? Screen is edible, madam?
Yes, sir.
Yes, sir. It is visible and also we can hear you also, sir.
Pardon, madam, because I have been little bit practice has not gone due to pandemic, so little bit.
Yes.
Madam, I think it's visible now. Thank you very much, madam, for giving a nice introduction about me. And thank you very much for giving an opportunity. They're all students. A very good evening. And good evening, madam, to you also. Just I wish to share my views of quantum mechanics and statistical mechanics and with few applications in this webinar, madam. Before going to the start introduction, exactly what is exactly meaning of classical mechanics and what is the relativistic mechanics, what is quantum mechanics and what is quantum field theory. If we look into that, if a particle is approaching almost speed of light, then what happens? Whatever the classical mechanics reduces to relativistic mechanics, if you say. And if the size of the particle is less than 10⁻⁻m, then the classical mechanics goes to the quantum mechanics. And if both speed as well as size of the particle is maintained, then we call quantum field theory. This quantum field theory is nothing but as little bits deals about the statistical mechanics. So the quantum field theory is governed by all three kind of things. Then this is called as statistical mechanics, which is related to that. So why quantum mechanics is best when you have classical mechanics? The quantum mechanics, the word quantum is derived from the Latin. The meaning is that quantama vulfut. I means I did the best. So I did the best of classical mechanics. Whatever the classical mechanics could not explain about the interior of the atom, the quantum mechanics made an attempt to understand about the interior of the atom. So they called I did the best, then that is called quantum mechanics. Little bit. If you go to the earlier centuries about earlier centuries, earlier century people used to have classical mechanics only the mechanics, because whatever I can see with my eyes, that is the physics. Whatever experimentally which is proven, that is called physics. So people were interested about the range of the particle and how, for example, a particle is thrown, what is the range and what is the maximum height which goes to that. So these people were interested about the Newtonian mechanics. This was earliest of 19th and 21st centuries. And after that formulation of the classical mechanics, to understand the interior of the atoms, people have attempted many kind of things. So modification of the classical mechanics, nothing but as the Newtonian mechanics, we call Lagrangian mechanics and Hamiltonian mechanics. Lagrangian and Hamiltonian mechanics together will explain about the all kind of energy systems and other things. So these are all things we study in classical mechanics about that. Coming to the quantum mechanics, first we go to the Bohr's theory. That is the first fundamental or called Bohr quantum theory, which is given by Niels Bohr about that. So what exactly this theory was? This theory says that when your hydrogen atom spectrum you have taken, the hydrogen spectrum is not continuous. Hello, you are following now? Hello? Hello?
Yes, sir.
When you take the spectrum of the students should speak, then only I can understand, right? So if you take the hydrogen spectrum, what is the spectrum is not a continuous, it is a kind of discrete kind of thing. So what does it mean? For example, if all energy levels fall in the first orbit, you call Lyman series, and of the second orbit you call Balmer series, and you call third orbit called Paschen series, and fourth orbit called Brackett series, and the last penultimate series is called Pfeiffer series. These are all things we have studied in BSc. Just I'm putting a kind of a bridge to that thing. Okay, so this is called how to explain about this. This explanation was not given by classical mechanics because where energy is continuous in classical mechanics, whereas in quantum mechanics, you said that energy is a discrete, it's not continuous. It's a broken kind of these lines. So how to explain this? For this, we required a model. In this Rutherford model, there's nothing but the old quantum theory. He put it into the put it into the four kind of concept. What is called stationary orbit? He has given stationary orbit. As long as this electron is rotating along orbit, it is a stationary. It's called stationary orbit. And second is called quantum condition. Stationary nucleus, non-relativistic motions, transitions, frequency conditions. So all these things we have studied, but just I will give you a brief of that. Any transitions taking from one orbit to other orbit, it gives energy, right? It gives energy. When it goes to that, it takes energy, it's to go like that. So what does it mean? Giving energy and taking energy. When higher to here, it emits energy, and from lower to higher, it takes energy and giving to that thing. So this is given quantum conditions. And this is called transitions. So E2 minus E1 is equal to HU. This is called E2, then you call E1, then E2 minus equal to, this is called frequency conditions. Bohr also introduced another kind of things called, whatever these electrons rotating along the nucleus, it has MVR. That's called angular momentum. MVR is equal to NH by 2 pi. This also we have seen about that. So I'm not going to details about that. So Bohr has given all this kind of things. What is that? Allowed stationary orbit. He has given one thing. And second thing is called frequency conditions. And third is called the stationary orbit. And it's called stationary nucleus. Nucleus is a stationary. It's not moving like that. It's always in terms of a non-relativistic motion of the electrons. Those actually, once again, put into the correspondence. What is correspondence? Correspondence between the classical things. That's called Bohr's correspondence principle. What is the linkage between Bohr's classical spectra and the quantum frequency. Classical frequency and quantum frequency, the relation is given this. So this relation is nothing but as Bose correspondence principle, correspondence between classical and quantum. So in this, why I want to tell you about that, here it has introduced a selection rule. Strictly speaking of that, this classical frequency V is equals to Z square RC 1 by N square by N2 square, right? So if you take LCM, this becomes N2 square minus N1 square by N1 to the power 4. Okay. If N2 minus this is nothing but as N2 minus N1 into N2 plus N1. Hello? So this numerator can be represented by N2 plus 1, A square minus B square, right? N2 square minus N1 square. This can be represented by N2 minus N1 into N2 plus N1. Okay. If N2 minus N1 is nothing but as delta N, if you consider 1, then only can say the classical frequency is multiples of quantum conditions. So this explanation, more or less given explanation about the correspondence principle, then thereafter the quantum mechanics has started beginning a few things. Whatever you had discussed about the simple Bose-Rutherford model, and after that correspondence principle. Now coming to the fundamentals of the wave mechanics, after de Broglie of studying of the light waves, so understanding about the particle nature as well as the wave nature, we consider that every particle, every material particle has dual nature. For example, dual nature means dual nature means if you want to understand wave light, interference phenomena and diffraction phenomena can be understood by the wave nature. Okay. For example, quantum photoelectric effect, Compton effect, all other kind of things can be explained by the particle natures, right? So this kind of things we'll see that. So quantum theory is nothing but as emission and absorption of radiation in terms of quanta. Quanta means particles or wave packets, what is a quanta? So de Broglie, this taking the hypothesis of the wave nature of the dual nature, he put into that. So every matter waves are nothing but as every matter, nothing but as you call the electron or a proton, you consider the material particle. This material particle having lambda is equal to h by mv. So what is lambda? Lambda is nothing but as h. Lambda is nothing but the wavelength. H is nothing but the Planck constant and mass of the particle and velocity of the particle. So a linkage between, he established a linkage between lambda and the velocity, lambda and particle velocity. So he also put that stationary orbits. What is stationary orbits? Electron is rotating this thing. As long as no energy is dissipating or no energy is taking, the electron is rotating like that. They're called stationary orbit. In the stationary orbit, what is this angular momentum J is equal to nh by 2 pi. So this is called stationary conditions. What given by Bose, he has taken this hypothesis. In this hypothesis says that J is equal to mvr is equal to nh by 2 pi. So this relation was given by de Broglie for stationary orbit by using for stationary orbits of Bose assumption. Is it okay? Hello? Hello?
Yes, sir.
Yes, sir.
Yes,
So
sir.
based on the Bose assumptions, what de Broglie said that he established a relation between J is equal to mvr, which is equal to nh by 2 pi. Okay. Now real quantum mechanics starts over here. For example, you say the material particle. So what is a material particle? A particle which is in a velocity is called material particle. I already told you. So material particle lambda, which is equal to h by mv, which is nothing but as h by p. P is nothing but as mass into velocity. We call momentum, right? So lambda is equal to h by p. This is, you say, that material particle kind of things. For example, energy. What is energy? Energy is nothing but as h nu. So h is Planck constant. V. Why you multiply Planck constant? Because classical energy, if you multiply Planck constant, the energy is formed to be discrete, means broken into many kind of pieces. E is equal to h nu. So mu is equal to E by h. What is energy relation? E is equal to mc square relation. So E is equal to mc square, which is equal to E is nothing but as h nu. You are putting h nu here, mc square only. So V frequency nothing but as mc square by h. From this relation, if you look into that, if relation becomes that, V nothing but as a material particle, which is equal to mc square by h. De Broglie wave velocity, if you say V is equal to lambda into frequency, this is called V. So U is equal to what? Lambda into frequency. This is called material particle velocity, nothing but as phase velocity. This is called particle velocity. You call phase velocity, then you call particle velocity. If you look into this equation, U is equal to lambda. What is lambda? Lambda is nothing but as h by mv. This relation I'm putting here, right? Then after that, frequency, what is that? MC square by h. You put into that c square by v. So phase velocity or wave velocity is nothing but as c square by v. So from this, we are getting to unexpected value. So what does it mean? V is less than c and u is more than c. We cannot have two velocities like that. So the material particle here, de Broglie, considered to equivalent to single wave train, nothing but a phase velocity. So material particle considered only single wave concept. So de Broglie concept explains about the single wave concept. It could not explain the wave packet theory. That is a failure of the old quantum theories about that. Now, what is Irving-Schrödinger has given? Irving-Schrödinger has given that, postulated to that, a wave packet is nothing but as a wave packet. So large number of waves are consistent that. Large number of waves, that wave packet is nothing but as equivalent to group wave or wave packet. So if you consider wave packet only, we can understand wave nature. If you consider single wave train or nothing but a single particle velocity, you cannot understand about the quantum mechanics because wave consists of packet of waves. Packet means what? Packet consists large number of waves. So large number of waves are there. That's nothing but as packet velocity. So packet velocity and nothing but as this explains about that. So single wave train cannot explain about the wave packet. So multiple wavelengths or large number of wave trains which explains of the packet velocity. This explains about the Schrödinger wave equations. So once again, I'm repeating that if you have single wave, you can explain only de Broglie. Whereas multiple of waves are there, you cannot explain the concept. Therefore, Irving-Schrödinger made contribution that single wave cannot explain about that. A group of waves are there. A group of waves nothing but as wave packet. And he explains about this has different kind of phases. Altogether, they call group velocity called Vg. They call it Vg. Okay. So up to here, clear? Hello? Hello?
Yes, sir. Yes, sir.
These all BSc stuff. So I'm putting into that. Okay. Now,
Yeah.
Irving-Schrödinger made a beautiful equations called time-dependent Schrödinger equation, time-independent Schrödinger equation. So this is well-known equation minus x square by 2m. You call del square psi plus u, you get psi into a psi. Okay, this is also this nothing but the potential energy. So it's just minus x square by 2m del square v psi plus is equal to e psi. Similarly, this time dependent, time independent. Here, there's no time part. Here we have time. Time is there. So time dependent. It's called time independent Schrödinger equations. Okay, we go a little bit further. That here you have psi. In this, what is this? There's nothing but a second order differential equation. This second order differential equation explains about the wave nature. That both wave nature. Wave nature is nothing but a particle in a motion can be explained by Schrödinger equation. Any particle, whether it's electron, you call proton, whatever the wave particle in a motion, this can be explained by simple Schrödinger equation. Okay. But here given what is psi, this is very, very important. This is a wave function psi. Wave function has to be defined. So what is exactly wave function? A wave function, nothing but as it should be finite everywhere. It should be single value and it should be continuous. So what is the meaning of continuous? Finite means what? It should be convergent. The function should be convergent function. It should be known value. It can be soluble. Then only can wave function can understand. If it is insoluble, you cannot define wave function. Is it clear? If wave function is undefined, you cannot define wave function. It should be finite and should be a soluble kind of thing. It should be single value and must be continuous. What is not continuous? Psi 1 is equal to psi 2. When it's continuous, its derivative also continuous. Dou psi 1 by dou x is equal to dou psi 2 by dou. This is also stated that. So probability is equal to nothing but as integral psi into psi complex dv is equal to 1. So probability means what? Finding out exact or the position or velocity or position or x or moment velocity. So that is equal to 1. P is equal to integral psi complex psi into dy. So this all things is given by Irving-Schrödinger about that. For example, if it is not 1, it is n, then what is called unnormalized. So the wave function, this is normalized. Unnormalized, you can do by multiplying and dividing by constant. So P can be represented by, if it is n, you write in that. So it can be represented by 1 by n is equal to psi complex psi dv is equal to n. So that nothing but as 1 by root n. This is called 1 by root n, right? So in this, what are the applications of the Irving-Schrödinger equations? Very good example is called quantum tunneling. So what is quantum tunneling? For example, electron or any particle or any motion. This can be explained by a kind of wave, right? When it comes, it tunnels. When coming, and amplitude decreases, comes like. Okay, so this concept explained about what do you call the nuclear alpha decay and other kind of concepts. So what is that here now? For example, the wave particle is coming over here, having some amplitude here. After that, if you want to cross over here, so what happens? It goes over like that, come down here. So quantum mechanical equations exactly gives about the tunneling phenomenon. This is called tunneling phenomenon. Okay, the particle tunnels about that, right? This once again depends upon the height of the barrier and the breadth of the barrier. These are two parameters are very important. If breadth is very high, then tunneling decreases. If height is more and infinite, tunneling is not possible. So with the controlled X and controlled the barrier, what you call it tunnels about that. Coming to the applications, this is very recent application we have, STM nano instrumentations, where we have a tip, we have a piezoelectric material, this is a piezoelectric material, the tip is there, this is the surface of the material, this is called barrier kind of things. So if you have barrier, so what happens? Current flows. When current flows, then you can understand the morphology of the materials. Current flows means what? If it is barrier, current is not flowing. If it is quantum mechanical, is not there, there is no barrier. So what happens classical? When wave is coming over here, it's scattered. It won't penetrate, right? Current will not flow. Whereas here, the wave is passing through here and tunnels like that. So what happens? You can sense the current. When you sense the current, what happens? These are all wells. You consider wells. Then what happens? Then you can sense the morphology. You can understand the morphology of the materials. Okay. So this is very good example of the barrier. Other things, if potential in the system is not exactly soluble or it is a kind of puzzling task, then approximations are needed. What are approximations? There are many approximations in quantum mechanics. What is called time-independent approximation, time-dependent, Wilson-Cramer, Billowin approximation, and variation methods, and blah, blah, blah. So time-independent perturbation theory will explain about the concepts of the how, Schrödinger equations explains about the correction energy term and connection wave function term. All these things we'll study about that. Time-independent perturbation theory explains about the corrections in energy terms and corrections in wave functions and other. Time-independent perturbation theory explains about the, especially the called Fermi golden rules. So what is the Fermi golden rule? Transition probability. So transition probability is proportional to the square of the matrix elements and other things we study in time-dependent perturbation theory. WKB explains about the linkage between classical limiting points and quantum limiting points. All these things explained by quantum approximations. Okay. Hello. Hello.
Okay, sir.
So once again, I'm repeating that quantum Schrödinger wave applications explains about exactly about tunneling phenomenon. From this tunneling phenomena, you can have a lot number of applications about that. So this current is passing through that. This is like that. So what is happening here? It is one potential there, one potential there, one potential there. When current flows, what happens? It's the surface morphology will scans. If current is not passing, you cannot scan the morphology. So this is the application of the exactly tunneling effect. If it is classical, what happens? The wave is coming over here, it's scattered, it won't tunnels, right? What is particle? Particle flow is nothing but as flux. Flux is nothing but as you call current. So that nothing but as electron is in motion, nothing but as current, right? So this current concept, that means continuity, I call it continuity. Based on the continuity, you can study the morphology. This is exactly the applications of the tunneling effect. That is called nano instruments. Presently, what they are doing. With this matter, I want to go once again repeating about that. Many theories have evolved. So just we recollect from the olden days how they really sacrificed their lives to understand about that. Just to understand about quantum theory. I'm once again repeating that classical physics at that time, at the early of 19th century, people used to believe what they see with eyes. That is only physics. If you talk about the interior side of the atom, they won't believe because we cannot prove experimentally how electron is there and how nucleus is there like that. For that, conceptual physics is required. So how the conceptual physics was built at those times, just we recollect about that. To understand the quantum theory, we require two kinds of hypotheses. What are that? One is mathematical, one is conceptual kind of things. Conceptual is very difficult to understand. You cannot put any concepts because we do not know what is atom and what is electron. Conceptually, you cannot develop it. So only required mathematical kind of thing. Okay, next. What are the physical entities? Physical entities nothing but as particles, matter nothing but as particles. Particles are nothing but as what you call electron or whatever. Second is radiation. Radiation nothing but as energy, that nothing but as corpuscles. To understand this, two interpretations was made. One is called Albert Einstein interpretation and Niels Bohr interpretation. Albert Einstein interpretation always said that statistical kind of thing, whereas Niels Bohr, where his born place or his research laboratory, Copenhagen place of the in London. So Niels Bohr interpretation or Copenhagen interpretation they call Niels Bohr interpretation or Copenhagen interpretation. This is called Albert Einstein interpretation or statistical interpretation. Let us see one by one what they are. Hello.
Hello.
Chappanamma. What is that?
Sir, you can continue, sir.
Some disturbance is coming.
Disturbance in between. Sir, you can continue.
Madam, these are class people only, na?
Class only.
Okay. So quantum theory is required, to understand. I'm talking once again, I'm repeating that. So earlier days, we do not have any evidences to prove what is existence of electron or existence of the nucleus. For that, how Albert Einstein really interpreted his theories, that we see how they interpreted in things. So to interpret that, two interpretations are there: Albert Einstein interpretation, which is called statistical, and Niels Bohr interpretation, nothing but as Copenhagen interpretations. Okay. So at that time, since they do not have an experiment, so they choose called tossing the coin. Tossing the coin means what? You raise a toss in the coin. From the tossing the coin, what you will have will get probability half. You will understand that. When you toss the coin, what happens? It will get heads or tails. So since they do not have an experiment, they want to choose tossing the coin. See how, silly it was, but those days, how they were struggled. Let's see, look into that. In order to prove the existence of electron or nucleus and other things, they choose experiment called tossing the coin. So tossing the coin, what Einstein says that probability is half. Half means either tails, half means heads or tails. So what is the head or tails? Nothing but is a fact. Fact is nothing but is a phenomenon, what you are observing. So observing fact or observing, do not observe any fact. So observing electron or observing not electron. So fact or not fact. So they want to put into by means of tossing coin. I'm talking about earlier 19th century about that. Copenhagen, Niels Bohr said that head or tails is a meaningless statement, because whether you get head, electron is there or electron is not there is a meaningless statement, right? So heads or tails is a meaningless statement. So if coin falls partially means in between, we cannot tell whether it's a head or tail. So this is a puzzling task. So statistical interpretations, only the interpretation can give you that, not the experiment. So Copenhagen and statistical results are individual case. You cannot explain the phenomenon of existence of electron or a nuclear, other things. So Irving Schrödinger made that another thing is called Schrödinger cat. This is another experiment he is putting to that. So what is Schrödinger cat? He put a box, he made a box and put a cat over here. Cat is the cat, it is there. And he made one cyanide bottle. This bottle, what you're observing is cyanide bottle. And you have, here is a hammer is there. By means of triggering mechanism, this hammer hits the bottle and cyanide comes out. So what you are putting that, Schrödinger said that he put a box in that, he put a cat over here, right? He closed the box and he put a cyanide bottle here. There's a cyanide bottle here. It is a hammer. You put a hammer here. By means of triggering mechanism, after some half an hour or after a few seconds or few minutes, this hammer hits the cyanide bottle and comes out. When cyanide, is a very poisonous material. When cat eats on that, it will die. This is die cat. So Schrödinger said that if cat put into the box and I put cyanide, after time t, then cat will die. Whether the cat is alive or cat is died. What is that? So this is what he was put into the experiment. Let us see the results. So this is a cat. After time being, what happens? It is dead. After cat, it is talking about cat is alive. Cat may alive, cat may dead. Cat may dead, cat may alive. Once again, repeating that. Cat may alive, cat may dead. So what is the meaning of that? Alive and dead, the two things are events. Dead cat is an event and alive cat is also event. So event taking place. Now event is taking place. So many interpretations are there in this. So let us see next cat. So what is dead cat? What is ancient cat? We do not know. We cannot tell about the experiment. And people talk about why cat? Why cannot be rat? Why cannot be elephant? So people talk all these kind of questions. Why are you putting cat only? Why cannot dog? Why cannot elephant? So this conference in that debate between Einstein and Niels Bohr made a very arguments. In that, Albert Einstein made a beautiful experiment. This was resolved the paradox. So what is the paradox? Whether the cat is live or cat is dead, we want to inform you that. You cannot explain by this experiment. So we want to existence of the wave nature. So Einstein made a kind of experiment called thought experiment, THOUGHT. Sorry, I was spelling mistake. Thought experiment in that. So what is the thought experiment? If you put a source of light, you have two states, A and B. States are there. If A is closed, you get here. If A is closed, you get B here. If B is closed, you get here. Right? So this is the experiment. If A is alone, you get this kind of interference. If B is alone, you get this kind of P. If both slits are open, then what happens? You will supposed to get classically this kind of this. You got it? Hello? If slit A is open, what happens? You will get supposed to get this kind of pattern. Right? Slit A is open, you are getting this kind of pattern. If slit B is open, you get this kind of pattern. Okay. If two slits are open, you are supposed to get this kind of pattern, dotted line. But what is exactly happening? You are getting this kind of pattern, right? This kind of pattern. So what is meaning to say that you are explaining this kind of wave nature, establishing the wave nature, right? So the wave nature is not like classical kind of thing. It's a quantum mechanical wave nature is coming to that. So this thought experiments provoked many ideas into that. So what many ideas now? Here I'm coming to that. Here, dead cat. Sorry, this is dead cat. This is alive cat. So what is happening now here? This alive means constructive interference. Dead means destructive interference. So cat is nothing but a wave function psi. So psi can have constructive interference. Psi can have destructive interference. Therefore, this constructive and destructive interference together explains about this kind of phenomenon, right? Wave nature about that. So this cat is nothing but a wave function psi. Clearly understand that? Hello? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, then I say
Yes,
that
sir.
otherwise I am sleeping. So dead cat is nothing but as what? Destructive interference. What is live cat? Constructive interference. This is nothing but as wave function psi. So this make a remarkable revolution in quantum mechanics theory. So what they put that? These all debate made in Slovak conference in the year 1927. It's called Slovak conference about that. If you want to read further, you read Tankapan Quantum Mechanics. He explained all these things detailedly about. Please read that. You will really get interest toward this subject. So what they say that the fundamental equation of quantum mechanics, what you call psi, requires various cases of motion, interaction, and microparticle Schrödinger equation. How Schrödinger is formulated this wave function psi, it's really a marvelous contribution made by Irving Schrödinger called psi. Einstein's interpretation that the laws of quantum mechanical statistical behavior. See how he added one step ahead. He introduced a word called statistical. At that time, statistical does not know. He said a statistical character. What is the meaning of statistical character? I'll tell you after that. Now, you just listen about statistical character. So they concern not only one single system, but aggregation of large number of individual systems and repeated measurements only gives a solution. See how Einstein, a matured way of telling about the same results in a fashion without any experimental evidences. So to understand the laws of quantum mechanics, what you require? You require statistical character. Means what? You require either a collection of electron particles or collection of proton particles. Statistical, identical particles you require. You cannot club both the things, right? So statistical character. So statistical characterization required, and aggregation of all the systems, a series of repeated measurements only solves the what your quantum paradox. So this has given by Einstein in Slovak Conference 1927. Okay, it will be further if you go there. So they called Einstein, Podolsky, and Rosen paradox, EPR paradox. They call very important paradox. Really, this paradox made a revolution both in quantum as well as statistical. So what he says that EPR paradox 1, EPR paradox 2. Every element physical entity must have counterpart. What does it mean? If psi is there, there is a psi complex. Wave function psi is there, psi complex is there. Dead cat is there, alive cat is there. Psi is called psi complex. So every element means psi is there. There exists psi complex. So one paradox you are putting into that. Without disturbing that physical quantity, psi can, for example, 1, 2 is 2 interacting system. So this one interacting system, plus half, another minus half, minus, minus. See, at that time, Albert Einstein made minus. Actually, it should be supposed to be plus. So later on, statistical mechanics were developed. So what that does is called antisymmetric function. Minus means antisymmetric function, plus means symmetric function. So antisymmetric wave function can be explained by electron, and symmetric function explained by photon particles, nothing but as boson particles. So boson particles having plus here, and antisymmetric function they have minus. So I do not know, we also do not know how Einstein at that time, he really knows that how he put plus or minus. If you put plus, it is called boson. If you put minus, antisymmetric, nothing but an electron function. So electron function or interacting two function can be explained by antisymmetric way. So this is called minus. But Einstein was really a little bit ahead when Bohr's theories, and he made at that time only why it is meaning of symmetric and antisymmetric functions, other things. Yes, you read these letters which was wrote by Einstein as well as Niels Bohr. So see that. Heisenberg, Einstein wrote a letter to Schrödinger and as well as Niels Bohr. Schrödinger is a student of Niels Bohr, therefore he writes in Schrödinger, so Bohr's letter. So what is that? The Heisenberg-Bohr tranquilizing philosophy to delegate, contrived. So what is the meaning of that? You read this at a meeting. What is the meaning of that? So he has made a gentle pillow so that you cannot arouse so easily. Means what? You are sleeping. You're not seeing really what quantum mechanics is that. Simply you made some kind of postulates, not believing that what is the meaning of psi and psi complex, and what is the meaning of dead cat and what is a live cat, and what is the meaning of constructive and destructive interferences and other things. So simple by old quantum theory, we cannot understand what is the meaning of exactly quantum mechanics. So he writes, and he is criticizing, in fact, Niels Bohr. So what is that? You have provided a gentle pillow. True believer, which cannot easily arouse. So you cannot come out from the sleep. So you are sleeping, having a gentle pillow, not seeing exactly the evidences. Based on the criticism, and Niels Bohr replied to his letter so beautifully that on Arrive's very implausible theoretical conception, if one attempts to maintain thesis, statistical quantum mechanics theory in principle capable and providing complete description of the individual system. So Niels Bohr agreed that the statistical quantum mechanics principle, and it gives you complete description of the pictures. Whatever the difficulties that can be solved by assuming the quantum mechanics with the help of ensemble system. So this concept is given by this letter wrote by Niels Bohr to Albert Einstein. So Bohr was agreeing that what is that? Statistical quantum mechanics is only the explains about this kind of paradox. What are the paradox we have? So this is about 1920, where the early beginning of the quantum mechanics about that thing. Richard Feynman, who is really a Nobel laureate, he also says that where did we get that equation from? I mean, talking about the Schrödinger, that how he modulated psi. It came out of the mind of Schrödinger. How he put it made psi. It is not possible to derive from anything now. So psi derived from the Schrödinger contribution is really modest contribution. What Richard Feynman says that how he got from his brain, how he triggered from his brain. So that was really a puzzling at that time. Now this is simple harmonic motions, what I'm telling you about that. So simple harmonic motion, what classically, this is quantum mechanically. So what is that? A stretching ball, coming ball. So these two things are simple harmonic nature. Now, what is this? This is a real function and imaginary function. Blue is a real and this is called imaginary function. So what happened? These all states, stationary states, so independent of time t. But whereas this is moving, right? This function is moving. This is called non-stationary state. This example of stationary states, all this is called stationary states. Stationary states in terms of quantum mechanics. What is that? It is independent of time t. Time t independent. Whereas these things are time dependent or nothing but is moving with stationary state. So examples of stationary states and non-stationary states, sorry, examples of stationary. These are two things. Okay. Next, this is classical picture. These are called quantum pictures of stationary and non-stationary. See here now, psi 0. How this moving? Like this. So this explains the probability. So all this oscillating in between, all these real and imaginary parts are oscillating here. Blue gives real and another is called imaginary. So this explains about the probability of the system. Okay. Now, after the contribution made by both main Albert Einstein and Niels Bohr, Dirac required, he want to formalism of quantum mechanics, he chosen a kind of mathematical language. So Dirac's contribution really made another step. This is the language of quantum mechanics. What is the language? The mathematical language about that. So first you go to that linear vector space. So linear vector space is really given by mathematical equation. It is not connected with physics, but this linear vector space we adopted in quantum mechanics to express about your wave function, other things. Let us see what is exactly a linear vector space. A vector can be represented by what? A1, E1, A2, E2, plus A3, E3. What are A1, A2, A3? Nothing but as scalar quantities. What are E1, E2, E3? Nothing but as bases. So a vector can be formulated on the representation of the basis vectors. So E1, E2, E3. Based on the basis vectors. What are E1? E1 is along the x-axis, E2 is y-axis, E is at unit vectors. Unit vectors along the x-axis, y-axis, z-axis. What you call E1, E2, E3. They're unit vectors. E1, E2, E3 are scalar. So a vector can be formulated based on the basis. So all these bases that can be formulated means what? It can be designed or it can be given a value or given an explanation, or a wave vector can be explained or can be constructed by means of all bases in 3 dimensions. There are E1, E2, E3 are nothing but as a components of vector. Already I told you E1, E2, E3 are unit vectors or nothing but as a basis. Okay. Now this you're talking about 3-dimensional spaces. For example, A is nothing but as can be represented by A1, A2, E3. That is nothing but as a column matrix. Whereas G1 unit vector. X-axis, so X is present, Y is 0, Z 0. E2 is what? Y present, X 0, Z 0. E3 is what? X 0, Y 0, and Z is present. So they are all unit vectors. So A is A1, A2, A3. A vector components are A1, A2. I am talking about mathematics, no way concerned about physics. Let us see this fundamental of that. So you call E1, this is called E2, this is called E3. Okay. A vector can be represented by components A1, A2, A3, and B1, B2. For example, this is a vector, this is also a vector. So a vector can be operator. So this operator nothing but as a scalar product or nothing but as an inner product. So what is inner product? Operation between two vectors, A and B, right? Operation between A and B, you call it scalar product, also called inner product. Mathematically, they can define inner product AB with this called open parenthesis. It gives you B summation over I equal to 1 to 3 AI BI. Hello, are you following? Well, once again, repeat that. Hello. So
yes,
what
sir,
is
yes.
that?
Yes.
What is that? In order to understand quantum mechanics, we require a mathematical language, right? The mathematical language means we have to choose mathematical language from the mathematics concept of it. So what they did is they took mathematics law. So this is pure mathematics, no way concepts. So what is the mathematics? A vector can be built up of all components of this, and these are nothing but as a basis vectors. So a vector here can be represented by what? The basis of E1, E2, E3 are the basis. The vector can be developed, it can be constructed, otherwise I can say. So for example, this is a vector A, vector B. When vector A and vector B is operating or interacting, this can be represented by this kind of open brackets, AB. So whatever you can open brackets, they call inner product or scalar product. Right? Scalar product is nothing but as summation of I into BI. What is I? Because 1 to 3, we are talking about 3 dimensions. So we called AI, BI, I equal to 1 to 3. So inner product or scalar product, which is operating between two, can be explained by this. But coming to our thing, we have n-dimensional vector space. Our quantum mechanics have n dimension, not single one dimension. So n dimension, how can you apply? Simply I equal to 1 to 1, ai bi. See here, you said that ai bi 1 to 3 dimension, right? Here you have n dimensional, so you're writing 1 to n, ai 3i, n dimensional space. So inner product for n dimensional, how can you write? I is equal to 1 to n ai bi. This is inner product of that. This is not suitable for quantum mechanics because we have whatever the wave function here, there exists a complex conjugate of that. So psi complex is there. So if you have ai complex, you cannot put inner product for mathematics. For us, what is happening? What is our first EPR paradox? If wave function psi exists, there exists complex conjugate of that. Psi complex is there. So psi complex having a same set. Therefore, if I want to put a complex b, I cannot, a complex is 1, b is 1. So a complex b inner product, you cannot put into these mathematical equations. Therefore, this mathematical equation has to be modified. This modified quantum mechanical equation is this. You got this? So inner product a complex b or ab can be presented by I equal to 1 to n ai complex bi. This is exactly the quantum mechanical definition of inner product. Mathematical inner product is what? Simply ai bi. For vector a and vector b. So here what is that? Wave function psi, wave function b. A vector can be formulated wave function. I'll come afterwards, little bit after that. So vector a, vector b. For example, it is a complex is there, then what happens? A complex bi can be represented by inner product. This is operating a or operating b. So interaction of ab. Interaction of ab can be represented by this kind of definition. This is known as quantum mechanical definitions. Okay. For example, b is equal to a. Same vectors are there, a. Then it can be represented by a complex ai, then you call mod a square, right? So this is known as Schrodinger representation. What is Schrodinger representation? For example, fg, nothing but a psi complex psi, you can say. So fg, f is a function, g is a function. From vectors, we have moving function. So,
sir, excuse me, sir. Sir, why should we take here complex, sir?
Where? Because we have said that I'll come after that, but now only I'm telling you, if wave function existing means there exists a complex conjugate. So I will come this term next transparently. You please hold on that because next transparent I'll tell you about that. If I tell you, sir, I will get confused. Okay.
Okay, sir. So, okay, thank you.
Okay. So what is I'm telling you that if there exists, you assume like that. If there exists any complex in that, for example, AB means what? All kind of functions on. If there is a complex here, it cannot fit into mathematics, right? That means what? You should have same properties. A complex cannot exist in that. You got that? A, B is there, set of same things, then it exists. If A complex is there, it cannot fit into the mathematics. It is different set. So inner product, if you have A, for example, have A complex, then you can write this. So this definition will require that. Okay. For example, AA, so if A is equal to B, you can say mod of A square is like this. For example, based on this, you are building this. Remember that based on this, the operation between A and A or interaction between A can also be represented by interaction of F comma G. The interaction of G can be represented by what? F complex X Gx. This is called Schrodinger representation. Remember that. Schrodinger means integral psi complex psi x into dx or data, whatever you call. This is called Schrodinger representation. So inner product of psi complex psi, I'll come after that. You assume that here psi complex psi. So psi complex psi can be represented by like that, or psi complex phi, you can assume that. Psi complex like that. So this is Schrodinger representation. Okay. In order to solve this equation, we require norm of the vector. So norm is nothing but as AA to the power 1 by 2. So norm, if you do squaring on both sides, you get 1. So AA is equal to, can you minus this? Oh, okay. If AA is there, N is equal to what? AA to the power 1 by 2. AA, inner product is equal to 1. It is normalized. Okay. Then if normalized means inner product is equal to 1. If it is 0, then you call orthonormal vectors or non-normalized vectors. So in general, how they write? A, you write here, AJ here. So this is nothing but as inner product of AI AJ. This is represented by delta I. Where delta I is nothing but as conical delta. If I is equal to J, then what happens becomes 1. If I is not equal to J, it becomes 0. Delta I becomes 0. So this is general way of representation of inner product of Aij if A is equal to B. Okay. Is it okay up to here? Hello?
Sir, screen share చేసి screen కనిపించట్లేదు.
Screen కనిపించట్లేదా? ఇదేంటమ్మా?
Yes, sir. Sir.
Students, please respond.
Is it visible, sir?
Visible?
Yes, sir. Visible, sir, and audible also, sir. You continue, sir.
If you have doubts, please tell me, because we are, enlightened to students to, I want to give, because quantum mechanics, people thought very complicated. So I want to make,
After the webinar session, you
an
ask
attempt
without any
to
doubts.
make easy. My attempt is that one. Okay. Next
Yes,
is,
sir. Continue, sir.
next, you have asked the question, right? Hilbert space. Now you said that quantum mechanics are followed Hilbert space. Hilbert space means what? At least one should be different. A complex function deals, at least should have that. Not all real functions. It should have at least psi complex. If you call Hilbert space. So Hilbert space is nothing but as it consists of set all psi. It should have at least psi complex. If that set is called Hilbert space. Hilbert space never exists in mathematics. It exists in quantum mechanics. Function psi is there exists psi complex. So Hilbert space only we can understand quantum mechanics. Is it clear? The earlier question you asked that. Hello. Earlier when girl asked the question, why you call psi complex?
Students, please respond. Sir is asking you only.
Yes, sir. Yes, sir.
Girl asked the question that why psi complex is there.
Yes,
We
sir.
are talking about that. Now,
Yes, sir.
in quantum mechanics, we deal psi function. So you want to
sir.
deal psi function, simple, the earlier concept is not useful for us. So Hilbert space, we adopted that. So Hilbert is also a mathematician, but he deals with psi complex also. But for Dirac adopted all these things. His whole contribution is really Dirac's. Dirac's contribution of the quantum mechanical or language of mathematical, all derived by Dirac only. All these things are Dirac's only. So he directly adopted Hilbert space. He said that from Hilbert space only you can understand the quantum mechanics, or nothing but a language to understand mathematical is nothing is Hilbert space. What is Hilbert space? Hilbert space is nothing but as infinite dimensional vector space called function space. The function space should have at least complex. One complex should exist. Once again, I'm repeating that. Infinite dimensional space is called linear space. All quantum spaces are linear spaces only. All space are space are nothing but a linear space. Linear additive space. Why you call linear? Function is adding to another function. So linear space. So all functions are space, linear space. So infinite dimensional, because n is there. So infinite dimensional linear space is called functional space. So if functional space at least consists one complex, then you call Hilbert space. Functional space deals with Hilbert space.
Hilbert space.
Is it clear?
Yes, sir.
Once again, I'm telling you that. So don't get confused. So we required infinite dimensional space because all quantum 1 to infinity, right? 0 to infinity, you write down. In equation, now here we are doing AB, but you put 0 to infinity.
0
when
to
you say 0 to
infinity.
infinity, you put d tau here, right? Volume space. If you put specifically AB, you put dx. Clear? Same thing.
Okay.
Same thing. If you put A to B, you put A dx. If you put 0 to infinity, you put d tau. Volume integral come into the picture.
Hello.
AB means what? Defined parameter along the x-axis dx. Okay. Now what is that? Linear space is very important. So linear space have called functional space. This functional space is nothing but a psi complex, or what is called functional space. So if at least one complex conjugate exists, then that is called Hilbert space. All quantum mechanics are Hilbert space only.
It's called
because
Hilbert space.
Psi complex exists. Without psi complex, there is no quantum mechanics. It is not set of psi. It is set of all psi and have it is psi complex. We have psi complex only that thing. So based on the mathematical language, Dirac has made formulated definitions. So what are the definitions? The inner product or scalar product of two function fx can be represented by like this. This is called Dirac representation. Dirac representation calls this open parenthesis. Open parenthesis means open brackets. This is small brackets. In quantum mechanics, remember that don't write these brackets whenever you want. In mathematics, you can write whenever you want. So don't write this kind of parenthesis and this kind of square brackets. They are meaning in quantum mechanics. So don't use these brackets and square brackets. You know square brackets are this kind of brackets. Square brackets, don't use that. Square bracket you put in quantum mechanics means commutation. When you put this kind of bracket means they are inner product. So F is operating on G or interacting G. F and G interacting. So FG interaction, this is Dirac representation. Dirac put in FG interaction in bracket. Schrödinger put this kind of psi complex. F is nothing but a F complex only here. Relax. F complex G. So F complex X, Gx, this is Schrodinger representation A to X into Dx. Okay. Now, function G is orthogonal, means the inner product is equal to 0. If G is equal to 0, then you call orthogonal. Inner product is equal to 0, you call orthogonal functions. Then go to that. If norm of the vector, for example, if F is equal to G, same thing, then you say the same thing while putting that. F to the power F is equal to 1. I'm skipping that. If norm of the function, nothing but as normalized, nothing but as what you call 1 by 2 to the power 1 by 2, which is equal to 1, then you call norm is equal to unity. Similarly, F is equal to 1. Square root of 1 is equal to 1 only. You apply square root here, or you raise square on that. So what happens is 2 get cancelled out. 1 square is nothing but as 1. So F is equal to 1. So what is that? Norm of the function is equal to unity, you call normalized. And if norm of function is non-zero, you call it orthonormal. So whatever the mathematics concept he has given, so this concept is adopted by Dirac and he formulated here. So this is called nothing but as formulated of what? Quantum mechanical things. So F, inner product F can be represented with this. So F complex J, this is nothing but a direct representation Fg, represented by G. So there's nothing but, you need not write complex here. Understood that. So we put Fb, is nothing but as we have complex over here. Okay. Schrodinger, you have to put complex here. Schrodinger, you have to put complex. In inner product, you need not put complex. It is understood. It is F complex. First thing is, always remember that first one is complex. Don't put complex here. First complex, then you call real function. So complex, real function. This is the way. So some textbooks they write also, we have some G complex also, but I said that it's a good practice, I can say. Good practice means a good way of learning science. So Fg, it is nothing wrong if G complex, some people will also write, but don't write that thing. You put first complex, then you put Gx. So here, complex is there. It is understood. Fg, this is called Dirac representation of inner product. Schrodinger representation of inner product is this. This you should clear it. Schrodinger definition is this, and Dirac definition is Fg. Okay. With this introduction, we go a little bit. Set of functions. For example, linear dependent, we call another linear dependent. So what is a linear dependent? For example, if for example it's phi x is 0, then psi is not 0, then you say you call linearly dependent. So linearly independent means psi is equal to 0. If so, for example, linear dependent function, we can easily put this kind of functions very easily. But very important is non-linearly independent, linearly independent functions. To understand linearly independent functions, we require function should be complete. So what is the meaning of complete? For example, this is one function, function. All these functions resulted by this thing. So the completeness can be solved by resultant of this, right? So instead of putting all these things, you put this. You got this point? Instead of putting all these incomplete functions, you can put one complete function. So what does it mean? Phi x can be represented by psi x and the formation of that. All these functions represented by this. Then completeness establishes. When completeness establishes, you can construct the functions. You got this point here? Two things. Hello?
Sorry, sir. That means all functions, the summation of all functions, it's represented as a single function. Am I right?
Yes, yes. Function x. Then if it is independent, for example, not solvable, these functions are, incomplete, independent functions, linear independent functions. Then what happens? In order to represent all these functions, you can construct only one function. So phi x can be represented by psi I fi. What is fi? Fi is nothing but these are functions. So all these functions, summation, simple, represented by C, phi x. If you know phi x, you can understand what is the dependent functions. Becomes linearly dependent function, independent functions. Okay, this is what I mean to say that. So here, Ci is equal to what? F goes to here, complex, F complex. Student, sorry, Ci can be represented by what happens? F 1 by Fi. 1 by Fi is nothing but a complex. So F complex phi can be represented by Ci. Is it okay? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Okay, sir. Understood.
Yes, sir.
So,
Yes, sir.
whatever they are called coefficients, whatever they call constancy, can be represented by what is that? Phi inner product of that. So you can also explain that thing. If it is simply Ci of x is that, it's a simple thing. If it is non-simple thing, you choose this kind of functions. Okay. With this, we'll go a little bit. I'll put to another important called Hermitian operator. Quantum mechanical, we introduce operators. So what is operators? Operators, nothing but quantum mechanical. I'll come after that. You first one, I'll put one postulates. So operators and wave functions are associated with it. What does it mean? It's a coupled phenomenon. Wherever your wave function is there, operator is associated with it. Here, operator A, psi, they're coupled. You cannot separate now. So whenever your wave function psi is there, operator is associated with it. So the first postulates of the quantum mechanics says that all physical variables can be treated as operators. So position can be treated as operator x, put on cap, x cap, momentum p, t cap, energy, okay, leave it. Total kinetic energy t cap. So all what are the physical variables, position, momentum, kinetic energy, all these things, they treated as operators in quantum mechanics. This is called first postulate. This thing I'll tell you after that, but before that, you see that equations. For example, A is operator, the wave function psi x. An operator operates on a wave function, gives a value called eigenvalue A and psi. Here A is called operator. In textbook, generally operator will write tick A or A under cap. Or tick means they put bold, very bold A. Bold means dark A, you can say. Very, make it very, what you call, right number of times on that, it becomes thick, right? So thick A, nothing but as an operator. Or you put simple cap on that. If operator A operates on wave function psi x, it gives eigenvalue and wave function. So the psi x is called eigenfunctions, when A is called operator and small a is called eigenvalue. Is it okay? Hello? If operator operates on wave function, it gives a value, eigenvalue.
Eigenvalue, small a.
A small a is eigenvalue. Where capital A is called operator. What is operator? D by dx is operator. D by dx of x to the power n is equal to n into x power n minus. What is that? So operator transform into that, right? So like that. So it is called A psi x is equal to like that. This is where n is equal to 1, 2, 3. All quantum mechanical operators are, most of these are Hermitian. So what is the meaning of Hermitian? It's a very, very important definition. Let us say psi mx, psi nx. Here represent that. Psi m means what? Wave function of nth particle. Psi m means what? Wave function of nth particle. So in Dirac's notation, you just write bracket m comma n. I have not written here, sorry, I forgot it. So psi m is nothing but as, this is what? Interaction, right? So interaction, if you want to write simply m comma n, you put bracket, means that they are two interacting. Okay? Now, what is operator A? Operator A is Hermitian. This is the definition. The operator A is said to be Hermitian if and only if it follows this rule. What is this rule? For example, integral psi n complex A psi n dx, if it is there, this can be represented by, if you put d tau here, okay, dx also nothing wrong here, but d tau is better, volumetrically. So minus infinity to plus infinity, you are putting only x-axis. Nothing wrong in that, but you put d tau is better. So psi m complex into A psi n d of, that can be reported. A is what? Why it is here? Hermitian operator. If you put operator here, A psi n complex. So A complex is nothing but as A only, right? Hello? If A puts it here, A psi m whole complex, so A complex is nothing but as so
will become
psi
0.
Psi n dx. If you write like this, or if you have psi n, if you put here, complex of complex is equal to psi n only. Psi n complex and this complex. Together they form psi n. A complex, psi n complex, they are putting here. Right? So if you write it like this, then A is called Hermitian. Okay? Hello?
Yes, sir.
Sir, just like a commutative law.
Commutative law, but don't say commutative law. Here now putting that Hermitian operator. Why you put Hermitian operator? I'll tell you one or two transitions after that. Okay. So if you write like this, if you operator, nothing but as Hermitian operator, I'll tell you that little bit. You give me 1 or 2 minutes time, then I'll come to that. Psi m complex A psi n, if you write like this, then this is called Hermitian. This is called Schrödinger representation. Whatever the first thing is called Schrödinger representation. In terms of Dirac's notations or bracket notations or whatever, you put it inner product notation. Psi m, already I told you, psi m complex is represented by psi m. It understood that is a complex. You don't write complex here, right? So psi m complex, A psi n. This can be represented by, you can put A here, simply psi m, comma psi n. If you write this, then A is Hermitian, if 2 is valid. You can also write this also like this. You make it this, way to that, to make complex or upper. Is it okay? It is Schrödinger representation. It is Dirac notations or inner product notations. Okay? Hello?
Yes, sir.
Yes, sir.
If you made minus here, then you call it anti-Hermitian. You call it anti-Hermitian. You can have the doubts now here. Why you have anti-Hermitian? These anti-Hermitian, all these things will come to understand about the time reversal. I'll tell you a little bit now here, put that. For example, electron is occupied in a hole, right? So if you have occupancy only, electron is sitting on that. Like you have got admission in BRAOE. How? You qualified the rank and you occupied your chair in MSSC. So there is occupancy. When you have occupancy only, has set into that, right? They call occupancy. Similarly, you have occupancy on that thing. So this kind of occupancy, they explained about that time reversal operators and other things, they require this kind of minus anti-Hermitian about that. I will come after that thing. So remember that if a particle is existing, means that you should have occupancy. So particles occupied into that, then only have that thing. So positron pair. How you call positron pair? Hole and electron put together the positron pair about that. So this kind of concept explained by successfully about this kind of things only. For example, you have mirror images of that. For example, what is that? Left becomes right, right becomes left, or spin plus half, spin minus half. That kind of things will explain by time reversal operated by anti-Hermitians about that. Anti-Hermitians is a complicated operator. We will explain about the reversal operators. But all quantum mechanical operators, what you have, all things are Hermitians only. So this is what we write that. Okay, you go further. These are two Hermitian properties. Just now they asked that eigenvalues of Hermitians are real, and two eigenfunctions operators belong to different eigenvalues. They are orthogonal to each other. So these two properties have Hermitian operators. So let us simple proof I'm telling you. Let psi m have two eigenfunctions. Let psi m and psi n of two eigenfunctions. Then you put a psi m is equal to a m psi m. This is what eigenequation. It's all eigenequations. And these two are interacting. So psi n, a psi m. So this is what you call interacting psi n function is there. Psi m function is there. Two are two interacting. They are operating A is there, right? So if two interacting, A is a Hermitian. How can you write? How can you prove that? So psi n can A psi m is nothing but as this A m into that. So you put A m. This is a value. This is operator. Remember that operator can put here, operator can put here, because operator and functions are associated with it. You cannot put operator here. Values can put outside of the brackets. Is it okay? Hello? Operator,
yes, sir. Yes.
Operator should be associated with their function. So you can put
Yes,
into
sir.
here only. Operator cannot put here. Cannot put here. So eigenvalues can put here because value cannot be associated with it. So our values can be dragged, can drag outside of the parentheses. Whereas operators, you cannot drag. Okay. This, since A psi n is equal like this, so you put am like this. Okay. If A is a Hermitian, so what is right? Can you write down? This is m is equal to n. Then what happens is becomes simply psi n, a psi n. So Hermitian, so you can put it here. So since you can put it here, so this complex, the whole complex here, so an complex. So what does it mean? An value, an complex. All values complex. So all eigenvalues are real. They cannot be imagined. They cannot imagine. So Hermitian operators are real eigenvalues. They cannot complex, right? All values are real values. Therefore, this is called Hermitian operators of real. I am skipping also. Similarly, can prove so that an cannot be equal. So this will be 0 here. So since here what is that? An is there. So two are equal. For example, if you put two different things, so what happens? An cannot be equal AA. So this will become 0. Therefore, these two functions are orthogonal. If two functions are there, here only one function is there. So you are putting n only. Psi m treated as n only, same function. Therefore, you are putting two eigenvalues. If two different eigenfunctions are there, then they are orthogonal to each other. You got this? Hello?
Yes, sir.
So two functions
Yes,
are
sir.
same functions are there. So same functions are there. They are putting operators are real. Eigenvalues are real. If two different functions, am cannot equal to am, you can say right am. Am cannot be equal to am. Therefore, this will be 0. If this product is equal to 0 means what? One should be 0. One should be 0.
Remaining will be 0.
This cannot be 0 because am eigenvalue is different am eigenvalue. So what would be 0? This would be 0. Therefore, they are two orthogonal functions. This is another good representation of the Dirac's made that. So Dirac's given inner product definition or Ket broad definition. Bracket, B-R-A-K-E-T. So bracket. So Ket notations. Every wave function, real function can be represented by Ket notation like that. One symbol like that, one less than symbol like this, right? So you put that, there's nothing but a psi A. So position of the particle is very important, not wave function. A, if you write here, means it is psi A. This is a Schrödinger notation. This is called Dirac's notations. Every real function can be represented by Ket notation. Every complex notation can be represented by ulta. Ulta means BRA notation. They call BRA notation. Together they call bracket. If you put first complex, then real, right? So complex you put in here. This real you are putting here. Together they call, don't write this, you put this kind of symbol I have written wrongly. So this is nothing but this symbol. So bracket notations. You got that? So every real vector can be represented by state vector by Ket notations. Complex can be represented by BRA notation. They call BRA notation. It's called bra notations. This is called Ket notations. Ket notations. This is called BRA notations. Complex conjugate. So if you put together, so first you call complex, then you put real. So this symbol come here, then after that this symbol will come here. Okay. This is called bracket notation. Then operator. Remember that operator should be left of the Ket notations and right of the BRA notation. Why? Because this is what A is nothing but a psi A, right? A can go inside also, can transform into here because it's a wave function. Wave function operator is associated with it. So A can also put it here. So can you put it here? If you put A here, it cannot go here, right? So the Ket notations always you put operator on left, and for operator for BRA notations you on right. Is it clear? These two things? Hello?
Yes, sir.
So Ket notation represented by what? All real vectors can be represented by Ket. Psi A, real vector, represented by Ket. BRA, the psi complex, whatever psi complex, can be represented by this BRA vector, psi complex B. Oh, I written wrongly. Huh? Okay, leave it. So psi, this is nothing but a psi A complex. So you write on BA, write down. That's better in fact. Okay, now this complex, so you put bracket also. Yes, sir, correct. This is correct. Psi A, psi B complex can be represented by A. Complex is what? A. Real is what? B. So the position of the particle is very important, not the wave function. So bracket notation AB is that. So this is inner product notation. This is Schrödinger representation. There is Dirac's notation. So three notations are coming here now. Clear? Hello?
Sir, here what is nothing but Ket notation, sir?
Ket is nothing but a real notation. This is called Ket. This is Ket.
Okay, or that is symbol.
No. This is representation I'm talking about. Every real vector you are putting in Ket notations. Okay. This is mathematical language. So don't ask me head doubts why you are using Ket. No, that's the meaning of doubt. So what I told you,
no, sir, is called that is symbol. Symbol itself.
No, you try to understand that.
Okay,
to understand quantum mechanics, we require mathematical language. One minute.
A and B is the this one eigen value.
Position particle. Psi A, position of the particle. Psi A.
Capital A is the operator. Small a and small b is the
position of the particle. Instead of psi A, you can write A. Don't write psi A. Psi A don't write in Ket notation. Just position of the particle you write down. See, don't ask me why you are writing like this. Because I told you why you are writing A like this. There's no meaning of statement. Why you are writing A like this? You cannot. This is called selection rules. So what does it mean? I mean, you have required a language, right? Based on the language, you build up the quantum mechanics like that. These are the fundamentals of the languages of that. So don't ask me why you are writing like this. So they made the notations of mathematical language required. So a Ket notation represented by like this, right? So every real vector can be represented by Ket A. Every complex represented by BRA A. BRA A means, so BRA A is not there, so BRA B. So psi B complex, this is called psi B complex. This is called psi B complex. You can put like this. Okay. Altogether, what is psi A, psi B? Interacting two functions or interacting two vector spaces, A, B, inner product of A, B. So inner product of A, B, you can also write down here A comma B. You can also write down here. You're not psi A, psi B. You can also write down brackets of A comma B, nothing but as psi A, psi B. You can also write down, but this is not good practice. Good practice is A comma B. So A comma B is equal to integral psi A complex psi B d tau, which is equal to bracket of A B. So this is called inner product notations or Dirac's notations. This is also Dirac notation. This is called Schrodinger representation. So Schrodinger representation is there. Dirac's notation is there. But strictly speaking, Dirac's notation is the mathematical notations of that. Still, German people, they follow that. Most of the French and other people, they follow that. But internationally, now the people are following Dirac's notation only. This is the mathematical language where you can explain all the wave functions and you can understand what is the eigenvalues. You can understand what is operators, all from this formalism. So Dirac formalism is the formalism for the representation of the quantum mechanics. So this is AB. The concept clear vachunda meeku. This is called Schrodinger representation. This is called Schrodinger representation, sorry. This is called inner product or A comma B. This is called Dirac's notation. Complex, ket, BRE. B, ket notation, ket notation. Where is A is there. So operators on right of A and operators on left of A of ket and up right of B. So these are the properties of the Dirac's notations. Is it okay? Hello?
Yes, sir.
Now, here see that A is a Hermitian to AB. So psi A means nothing but a psi A, nothing but a psi B. So complex conjugate like this. So if A is Hermitian, this is valid in terms of bra notations or bracket notations. Is it okay? AB operated that. So if B is go here, A is come here, A complex, then you call
will become
A
complex.
Hermitian. A complex nothing but A only. So this is called Hermitian definition. A operator here said to be Hermitian in terms of Dirac's, it is like this. Dirac's notation should be like this. Okay. I'm skipping about that. Now I'm taking to postulates. So postulates, just now you asked about that. What is the postulates? So postulate means what? Without any experimental kind of things, just I'm putting the following rules and regulations. Based on the rules and regulation, you understand the phenomenon. So that's called postulate. So postulate one. So before going to the postulate, I'm giving what is the wave function. So wave function can be represented by two ways: on position and time dependent, and momentum time dependent. Momentum and time, position and time. So wave function can be represented either by position time or momentum and time. So wave function can be represented. So wave function should obey the properties. What is that? It should be convergent, it should be continuous, it should be soluble, it should be single valued. All wave function properties should obey. Here wave function is nothing but a psi. Psi should be single valued, psi should be convergent, psi should be soluble, psi should be exponential decay functions, all e to the power minus like that. Then operators. Just now I told you, don't use this kind of brackets in quantum mechanics. When you use this quantum mechanics QR meaning to say that QR minus RQ, if you put bracket this. Okay, this is called classical brackets. So this is called Poisson brackets. This is called quantum brackets. So relation between classical and quantum differ by H curve. So quantum mechanical QR operators is nothing but as H cross multiplies of Poisson brackets. Okay. Now these are observables. Postulate 2 explains about the operators. So what are the operators? All whatever the variables, what you are talking variables, X is a variable. Okay, momentum is a variable, energy is a variable. They can be treated as operators in quantum mechanics. Wherever your X is there, you cannot write X as simple, you can put X cap. Wherever your momentum, you can put minus H cross by dou X. Okay, Px is there. If P is there, minus H cross there you have to write. So along the x-axis, you can dou by dou X. Along y-axis, you can dou by dou X. Along d by dou X, you have to put dou by dou X. If it is P total, then you can minus H cross there. E is there, you have to write H cross dou by dou T. So wherever you have P is there, in quantum mechanical, you have to change into minus H cross there. Wherever you have kept E, operator E is there, you should convert into H cross dou by dou T. Is it okay? Hello?
Yes, sir.
Yes.
So this is what classical representation is called quantum mechanical representations. Oh. Then expectation value. Expectation nothing but as average value or expectation value same there. So expectation can be represented by this kind of symbols. This kind of symbols. Expectation. So integral psi complex IA d tau is equal to expectation. It is for normalized. If it is not normalized, so what happens? You have to do this kind of formula. If it is normalized, expectation value is this. Expectation represented by like this. Expectation is soluble, the function soluble. Average value. Okay, average value or expectation value or one and say. So average value or expectation value can be solved. If it is normalized, this is the formula. If it is not normalized, this is the formula. Okay. Already told you what is eigenvalue, eigenfunction. So if function is not an eigenfunction, so function can be expanded in terms of superposition principle. So phi is not an eigenfunction, then eigenfunction can be represented by summation of all these things. Constructive interference, whatever you call summation of all these things. So it's called phi. So if you say make phi, then what happens? You can do that thing. If it is simple eigenfunction, you write that. If phi is not an eigenfunction, this phi is not eigenfunction, this you have to make by linear combination of all eigenfunctions, then becomes eigen, right? Non-eigenfunction can be by linear combination of this. Then you can solve it. This is called eigenvalues. And fifth postulate tells about the time development Schrodinger equations. So very, very important equations. I square delta by dou t is equal to x. So this explains about the time development of the quantum mechanics. So quantum mechanics, we have 5 postulates. You remember that. One postulate explains about the wave function. Second explains about the operator. Third explains about the expectation value or average value. And fourth postulate explains about the eigenvalue or eigenequation. And fifth postulates about the time development of Schrodinger equations. From that, your large number of applications are MRI, lasers, solar cells, and atomic clocks used in GPS systems where you do not have seconds. There are very, very, very milliseconds of that. So this is required all or advance of quantum mechanics, quantum entanglement. For example, two particles interacting to each other. And after that, they are departed. Then this kind of entanglement can be understood by that. Now, the modern physics all deals about the GPS systems and electron microphones and solar cells. All these are modern application. Already I told you what is scanners. This is scanners, different kind of tunneling there. So current is passing through it. So these are VI characteristics. So if you have large number of barriers, so these are nothing but wells. You are sending the current. This current, it is like this. You have one atom, then another atom, or different kind of wells. Your current is passing through it. The current penetrates it. How current penetrates? By VI characteristics, you can understand that. So the barriers can be explained by this. So what does it mean? You can understand the morphology of the materials. This is the application of the quantum mechanics. Shall I continue or hello?
Please.
You can continue, sir.
You can wind up with applications, sir.
I'll wind up applications. Yeah, these
You
are the
wind up with applications.
Means of the application of that. Because I put statistical also, we have to interpret of statistical. So see the cartoon. This is a very, very old cartoon there by the one of the Nobel laureate lectures. I took that. So Boltzmann and he and Pauli Enfest, they together contributed statistical mechanics a beautiful way. And after that, it is our turn to understand about the quantum statistical mechanics. After 1933, statistical mechanics was really turned out many applications where you can understand about Bose instant condensation and liquid helium and what is called the tunneling or what you call the Pontier effects and other things. All these things made by after 1933. So who was the building blocks? Building blocks was Boltzmann and Enfest. Paul Enfest and Boltzmann, after their contributions, the statistical mechanics was developed. So it was the cartoon made by those days. So after 33, people were really studying many things. Then understanding about the boson particles, understanding about the Fermi-Dirac statistics, all things was developed after, maximum contribution made by Boltzmann and Enfest, Paul Enfest. Then quantum mechanics was developed. This was a cartoon given by one of the Nobel laureate lectures about that. Now, what is really statistical mechanics? Statistical, already I told you, collection of particles. Now we call that. To understand about classical, you should have two kind of definition you come into physics. One is called microscopic and called macroscopic. Micro means what? Collection of atoms and ions called microscopic. Macro means what? Explains about temperature, that's called pressure, energy, all things explained by macroscopic property. What is statistical mechanics? Statistical mechanics bridges between microscopic and macroscopic. It makes a bridge between macroscopic and macroscopic, or understanding or linkage between microscopic and macroscopic. This is gained by your statistical mechanics. So bridge between microscopic states, µs, and macroscopic states, a connection. This is nothing but as for statistical mechanics. Okay. To understand this statistical mechanics, we require two things. What are they? Equilibrium. What is equilibrium? This will not change with time. So macroscopic system, isolated system, nothing but as does not change with time. This is called equilibrium. Okay. Now, what is thermodynamics? Thermodynamics is nothing but relation between system of equilibrium or collection of macroscopic particles. They call thermodynamics. So statistical mechanics is nothing but a bridge between what I told you that. So to understand statistical mechanics, we require what you call state. State is described by phase space. What is meaning of phase space? If you have momentum and position, they call phase space. See, what is coordinates? X, y are coordinates. To understand phase space, we require two coordinates. What are two coordinates? Position and momentum. X, P. If X, P represented by that, then you call phase space. So what is the meaning of phase space? Phase or phase space are one and same only. So phase space is nothing but a combination of position, means X, and momentum. X, P. If we have X, P coordinates, then you call phase space. So statistical mechanics require phase space. Phase space explained by X, P, position and momentum coordinates. If you have position and momentum coordinates, you can understand what is the meaning of phase space. Is it okay? Hello?
Yes, sir.
Yes, sir.
Yes,
So,
sir.
yes. So there are two kinds of phase spaces are there. What are there? Mu space and gamma space. If 6 coordinates are there called mu space, and 6 n-dimensional space are the gamma space. So what is linkage between gamma and mu? Gamma and mu is nothing but an n. So n times of mu space is called gamma space. Well, I don't get confused. Statistical mechanics require bridges between macroscopic and macroscopic states. To understand statistical mechanics, we require phase space. What is phase space? Phase space nothing but as having position and momentum coordinates. Then you call phase space. Phase spaces are two kinds. One is called mu space and gamma space. So the linkage between mu and gamma space is built up of n mu spaces. If you have n mu spaces, then you call gamma space. I will give picture. This is called pictorial representations. So this is called mu space. For example, we have what you call phase space represented by X, P of single particle. You represent it called mu space. All n particle system represented by simple this dot, then you call gamma space. Here, so mu space representation is like this. Gamma space is nothing but as what? Collection of n particles. The collection of n particles are here. So the representation like that. So if you put this kind of picture, this is mu space. If you put this kind of picture, they call gamma space. Is it okay? Hello? This is
Yes,
mu
sir.
space representation. This is called
Yes, sir.
gamma
Yes.
space representation. So gamma is nothing but as n times of mu. So if you collect n times of mu spaces, then represented by gamma space.
Sir, that means in all the directions, sir.
And all directions, 6 dimensional directions.
Yes,
So,
sir. X, Y, Z like that.
No, it has 6 dimensions. Okay, degrees of freedom. X, Y, Z. You call X, Y, Z only. Okay. But it
Okay,
has, speaking, 6 degrees of freedom. Okay, you don't go detail about that. So what I'm telling is the particles, whatever the representation of the atoms. If you have representation atoms like that, one single isolated, you call mu space. Mu tells about only single space. Collection of n particles represented by here. So mu is nothing but as single phase spaces. Collection of all single phase spaces. The collection of what? N single phase.
Nothing but orbital.
No, don't orbit. Don't go to orbit. Collection, nothing but as collection. All collection of single phase spaces. All collection of mu spaces. All collection of mu spaces called gamma space. And then nothing but as bulk అనుకోండి. అంటే bulk is nothing but as a bulk. You take bulk. Collection of all single mu spaces called
Yes.
bulk. So bulk representation. It's only representation, but it should be space. Means what? Momentum and position. Okay, momentum position. In mu space, you write simply P and X. Here, collection of P, collection of X. You put in brackets. So if you put brackets P and X, this is called gamma space. If you put simply Px, dots called mu space. Okay, this is called collection of space. Okay. This space once again division. So how they are connected? So this called division of space called area. So volume of the space is represented by dx dy dz, dpx dy z. All multiply 3 dimensions. You say dx dy dz d tau under coordinates, under momentum coordinates dpx dy dz. Together they call d tau. Remember that data is always greater than h cube. This is called point phase space. So one of the good thing is point phase space can be represented in the order of h cube. Point space data. Data is nothing but the point space. Whatever your point space represented by h cube. Okay. Then how these points are connected? That's called ensemble. Here we will represent that ensemble nothing but as collection of assembles. Collection of assembles nothing but as ensemble. What is assemble? Assemble is nothing but a collection of the particle. If you represent along one particle one way, that's called single system. Single system is explained about the collection of single system in axes called ensembles. Assembles. Collection of assembles is nothing but as ensembles. This is called gamma space. We are representing that data, single space of that. Okay. How they are connected this? To understand ensemble, nothing but as collection. This ensemble word derived from the French. So what does it mean that ensemble means collection of all these systems. So collection of all assemblies, or collection of large number of particles called ensemble, the definition. So Gibbs has given this kind of interpretation. So P and Q, so gamma space you're talking about. So this is simple representation of ensemble data. So NV. This ensemble categories, 3 kind of categories. What are that? Macrocanonical ensemble, canonical ensemble, and grand canonical ensemble. So what is a macrocanonical? If M, B, E are constant, then you call it macro. Right? This is called macrocanonical ensemble. Collection of all particles, simple represented by this gamma space in here. Collection of all large particles, simple by this. So this simple D gamma explains about all the systems. Right? So NV. So how they are interacted, how the collection of particles are interacted. So this explains about the microcanonical mapping. So in microcanonical ensemble, EVN is constant. So for example, here energy should be constant. So what does it mean? This separated by non-penetrable means there is no penetration will be there. So PEVN. So energy, volume, number of particles should be constant. Energy, volume, number of particles here constant, all should be constant. So P is a function of E. So what is P? Momentum is function of energy, and what you call momentum is a statistical and average property, and distribution is uniform. Okay. For example, if a graph is drawn between momentum and position having constant energy, this is called ergodic surface. Ergodic surface about E. This is called another ergodic surface E plus D. Okay. This concept you read a little bit in statistical mechanics, where you read that. I'm skipping about that. And another canonical ensemble is called canonical. So this is called macrocanonical, canonical, grand canonical. Here, what is that? EVN is constant. Here, what is that? TVN is constant. So what is that here? T means
Temperature.
Temperature,
velocity.
Volume.
No, not
Volume.
velocity, volume, number of particles. So temperature, volume, number of particles, TVN is constant. So collection of all TVN if you have, then you call canonical ensemble. What is macrocanonical? Collection of EVN is called macrocanonical. Collection of all TVN is called canonical.
Canonical ensemble.
Macrocanonical, micro canonical is deviant. Canonical is deviant. Next is grand canonical. Here TVN is constant. Here what is happening? Energy is not there. So energy exchange takes place, but not mass. Remember that. Here energy is not there. Energy is not there now. So energy can exchange take place. Here there is no exchange. There is no exchange energy. Here what is happening? E is not there, therefore energy can exchange and mass is not exchanging here. Okay, so energy exchange takes place means what happens? Temperature remains constant. When energy is exchanging, all temperature of the system is constant. T is defined system. E is energy, E can be exchanged but not temperature. Energy can be exchanged but not temperature. So energy can be exchanged but not temperature in canonical ensemble. In coming to the grand canonical ensemble, TV mu. So EV mu. What is that? Here, both energy as well as mass exchange take place. Energy can exchange place, mass energy exchange place. Here, only energy can exchange place. Here, mass also can exchange place. So, mu, chemical potential, ability to react. So, what is that? Reaction is taking place. So, ability to react. So, ability to react, mu is constant. For example, if ability to react is not constant, what happens? It becomes different case of. For this reacts, it forms another. Then what happens? Mu is not constant, right? So, mu should be constant. It becomes different. For example, so that's the reason you should have U is constant and T is also constant. So to understand ensemble average, X bar can be represented by like this. And for individual systems, you have X bar. If individual cells are there, then what average distance can be represented by X bar. And if divided into cells, this X bar represented by this kind of notations. And distribution is kind of this. These are three mathematical languages explain about average distance. If a cell is divided into cell, then the average cell value, and if it is distribution is there uniformly, then it is X times of Nx. So this nothing but the mathematical language explains about X bar values. So the aim of ensemble is to know number of systems or elements which are found in gamma space at any time. All elements are similar. I mean non-distinguishable. If it is distinguishable, you call Bose. If it is non-distinguishable, if distinguished, called Maxwell Boltzmann. If it is indistinguishable, called as Fermi or Bose. Elements are similar. So this kind of concept will come after the application of this classical mechanics. Another fundamental law, I'll tell you about that fundamental postulates of the quantum mechanics. Earlier we have quantum postulate, classical quantum postulate. This is called statistical postulate. Statistical postulate have only one postulate called equal appropriate. So what is equal appropriate? This is the definition. What is that? So any microscopic states will link with macroscopic. So the states are linked with that. So the macroscopic system is equally probable or accessible to the macroscopic states. Macroscopic states are equal. These are macroscopic states are equally probable. So this is called macroscopic state under equilibrium. So all the states are equally accessible. If you have that, then we call equal appropriate probability. So this is a fundamental postulate of the statistical mechanics. So what is fundamental postulate? Fundamental postulate of statistical mechanics called appropriate probability. Appropriate they call. So what is appropriate? It is the connection of the macroscopic states are equally accessible to macroscopic conditions. So macroscopic system under equilibrium equally accessible to macroscopic states. If it is obeys, then you call equal a priori. They call equal a priori postulate. Equal a priori postulate. These are one of the fundamental postulates of that. Okay. Then after that, so the basic postulates already I told you. After that, giving definition about the equal appropriate postulates and the definitions of the all these ensembles. So what happens? The development for quantum mechanics for statistical mechanics begin. So these are our basic postulates, which explains about the Boltzmann and Maxwell-Boltzmann statistics, and after that, Fermi-Dirac statistics we have, and Bose-Einstein statistics we have. Fermi-Dirac explains about the unsymmetric function, and Bose-Einstein statistics explains about the symmetric functions, and next is classical statistics called Maxwell-Boltzmann statistics called classical statistics. Here we put one statement is also taken by one of the PPT of the Nobel laureate. Said that after long struggling of the Maxwell-Boltzmann in 1998, after that, recognition was Maxwell-Boltzmann was there after 20 years. 20 years after, 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 20 years his death. Before his death, he was not recognized, and after death, Maxwell Boltzmann, he has really given Maxwell the solution because he is the founder for next two statistics, namely Bose-Einstein statistics and what called Fermi-Dirac statistics. So Bose-Einstein, Fermi-Dirac statistics. Who is the thought-provoking is given by him only. So after his development, Fermi-Dirac statistics and Boltzmann statistics have, developed. So this is equal appropriate probability. I'm skipping also that. So now statistics have four states of ensemble average, four states of equal a priori probability, and four states of equilibrium states, or occupies maximum states. After this development, so the thermodynamics and Einstein-Debye models and lattice theories and ideal gas behavior, all things was developed after his theories. And this last cartoon, I'm talking about this today's talk. So here, what you're observing, one monkey is playing, one monkey is breaking that, and one monkey is sleeping. So this is a particle. There's also a particle. There's also a particle. So if you call this all electron, the properties are different because it is sleeping. So it is playing. It is like that. So collection of this kind of particles cannot explain about a statistic. Collection of identical behavior, that explains about that. So this is called random nature. This classical nature, nothing but as Maxwell-Boltzmann statistics explains about that. If all are sleeping, yes, can explain about the one. So collection of particles doesn't mean that collection of all monkeys. So collection of all particles like that. The collection of all what you call identical or similar particles, then only you can understand statistical mechanics thoroughly. Collection of protons or collection of electrons or collection of neutrons, you cannot explain about the statistical mechanics at all. So collection of identical particles are very, very important. So if you have this kind of monkeys or this kind of things, you cannot explain statistical. So explain statistical should have identical nature or identical properties, that only explains. Simple collection of this will not explain about that. Hello, with this, I stop today's class. Can you have any doubts? Please ask me.
If you have any doubts, you can. Students?
Because it is more than that, because I think I will little bounce. I know that, but the result is skipping. So if you have any doubts about that, please ask me about that, so that I go to that. So what is the Maxwell-Boltzmann classical statistics? Identical particles. For example, you put red balls and yellow balls. They are not identical, right? That explains about your Maxwell-Boltzmann. If you all put red balls, you remove one red ball, put into the basket of red balls. So you cannot differentiate which red ball you have took and which red ball you have put into that. So these are all identical particles. So identical particles explains about you all your statistical mechanics. Particles should be identical and should be distinguishable. Where you can explain about Fermi-Dirac or Bose-Einstein statistics. Bose-Einstein statistics explains about what? Boson particles. Fermi-Dirac explains about your electron and other antisymmetric functions. So with that, you are last number of that thing. So these all developed by equal appropriate probabilities and all ensembles. See how the evolution was taken with mathematical concept, but the most highlight about the Albert Einstein, he put in CPR paradox, simple by giving one equation. What is that? Symmetric antisymmetric function. Really, no one knows that how Albert Einstein has given this kind of paradox. How he solved this paradox. No explanation will give it. After that, many theories have proven this. But how Einstein has written this, we really do not know. From one story is also there. When Albert Einstein was there, he used to use all rough papers. A rough papers collection from dustbin that produced 18 volumes. In that 18 volume, still people are studying from that. So he's really, you can say, for us, a great man, he really shown what is statistical, what is, quantum. With his help only, Bose has recognized, our Bose has really developed the statistics. With the help of Albert Einstein, he made Bose-Einstein statistics. So that is really a tremendous development, a tremendous contribution was given by our Indian physicist Bose with help of Einstein. So how Einstein he put, really no one knows. Please, I'm telling you, whenever you free time, you read Penkamp and Quantum Mechanics, From that, I think you really enjoy and you really read quantum mechanics with interest. You still Tankampan, all I took from Tankampan and a little bit of internet. Hello? Hello?
Students?
Sir, one question, sir.
Yeah, if you have any doubts, you ask to sir.
Sir, this one you are showing this blue and some kind of another color of waveform, independent and dependent waveform.
No, dependent. Okay, one minute. I'll tell you. How can I come this? Oh, animation. I come out. Okay. Tell me that. Animation, how can I put it? Here I go.
Yes, sir. That one is dependent and another one is independent, not like that.
No, don't get confused. So what I'm telling is, integral psi complex psi is independent of time. They call stationary states, right? Not dependent on time. So this explains about this. This what happens. The real and imaginary operating the same kind of things. So this is a non-stationary kind of thing. It's just a representation I'm talking about, nothing like that. This is a classical representation of harmonic oscillator. This is the representation of wave function. See, in quantum mechanics, we have psi real and psi imaginary. Real and imaginary. So real and imaginary functions oscillate like this.
Yes, sir. Yes, sir. One C and D is we can see that you are already told that mirror image. Let it be considered a phase shift.
No. Don't say mirror image. This is some wave kind pattern. A wave of time. If you draw the plot, position versus energy, you get this kind of wave function, right? Okay, I'll tell you like this. This is well and contact. You consider this well, right? Well, if you have only a ground state, you get only one wave function like this. One wave function like this. If you get two, we get two waves like this, right? The waves split into that parts. So what happens? This I don't have the graph, otherwise I'll tell you. Okay, this is a well. You put it like this. What happens? The wave will like this. You are seeing the cursor. Hello. Cursor, you are seeing.
Yes, sir.
You treated this as a well. See, clearly cursor. This is the well, right? Well, right? When n is equal to 1, what happens? The wave should be like this, right? So what does it mean?
Yes, sir.
So this is called classical limit. This is called quantum limit. At n is equal to fast energy level, classical and quantum are different. At high energy levels, both this classical and quantum will emerge. So this is quantum comes to classical at high energy levels. So that concept I'm putting into that. Actually, I forgot and I put into that. Is good. So the question now here, when you talk about quantum, you have real and imaginary. Already telling you. So the real and imaginary functions are putting into that. Depend upon time, independent of time. That's it. As a progressive. Here wave is progressive. Here wave is there only. The main particle oscillating here only. So they are stationary states. Okay, next.
Yeah, anybody? Let us conclude. Let us conclude.
Hello?
Yeah, if there are no questions, you can conclude, Usha.
Okay, ma'am. Thank you very much.
Madam, thank you very much, madam. Given opportunity.
Thank you, sir, for accepting this invitation, our invitation to give a lecture. Sir, your lecture is very wonderful lecture, sir. You are given precious time for us. And also, first of all, I would like to say thanks to our Pushpa Chakrapani ma'am, HOD ma'am, our Department of Physics, Ambedkar Open University. She only arranged this program, wonderful program. Thank you very much, ma'am. Sir, thank you very much, sir. Your wonderful lecture. I hope this webinar was very helpful to our students. And I thank each and everyone for attending this webinar program. And also, I thank the administration and the computer staff who have arranged this webinar. Thank you, one and all. Thank you very much, Prasad sir. Your wonderful lecture. Thank you very much, ma'am. Thank you. Thank you, everyone.
Thank you.
Thank you, sir. Thank you, ma'am.
Thank you, sir, ma'am.
Thank you, madam.
Thank you, sir.
Thank you very much.
Thank you very much.